Hey everybody, it's good morning. It's time to do Unit 5, the rest of the thermochemistry notes. So I figure if you couldn't come to class, we'd bring class to you. And we're working on energy and phase changes, and just a quick review. The first law of thermodynamics, remember that energy is merely transferred. If something is exothermic, it's given off heat to you, it feels warm to your touch. And if something is exothermic, the energy is actually being drawn away from you and into the chemicals. So that's the way it is. New information for today. We've got a little bit of some phase change discussion to do. And we have got some calculations to do. All fun stuff leading up to whenever we have class next. Oh, it's been a crazy winter. In any case, glad to see that you're here working on this. It's definitely going to make a difference when it comes time to the AP test. If you look at this I always call it a cooling curve. This is a heating curve. This would be, for example, a solid. And let's get the pencil tool going here. This right here is a solid phase. This, it would require energy to heat the ice, for instance, to actually give the molecules energy of motion. And once those molecules are moving fast enough, we can actually apply energy in part B here to break the IMFs. And that energy is called the heat of fusion. Once we get those molecules into the liquid form, then we can actually heat those liquid molecules to where they're moving fast and faster until we get to this plateau D here, where then we're adding the heat of vaporization, which is again further bringing distance between the liquid molecules to form gas molecules. So we have the heat of fusion here at plateau B, and then the heat of vaporization at plateau D. And you can take that even further, taking gas and superheating it beyond the 100 degrees boiling if you wish. Two equations here that are really important. This one is for all of the slopes, A, C, and E. This we'll talk about shortly. It has to do with the calorimeter heat that's absorbed by the calorimeter itself. And that's something that we'll be doing in lab. We'll talk about that shortly. This is to calculate the calorimeter constant. Again, something we'll be using in lab. Moving right along. The different calculations that you'll need to use along each step of the heating curve. Looking at question 1 here, it says how much heat is given off by water if a 250 gram sample of it with a certain specific heat drops in temperature from 35 to 15. So what we're getting there is if you have a sample of water and you would simply multiply that mass by the specific heat by the change in temperature, and that would actually give a loss of 20,900 joules. I actually have these two reversed. It should be T finals minus T initial. Looking at the next item, how much heat is required to melt 50 grams of ice at its melting point. This is a case where it's like in plateau B, you're actually at that point where you've already given ice all of its energy at its melting point of motion. You no longer can get it to move. You are actually having to separate the molecules from each other. So you're really adding the heat of fusion, 5.99 kilojoules per mole of ice, to change it into liquid at its boiling point, or I'm sorry, at its melting point. So converting grams to moles, because we need to multiply those many moles of ice to multiply it by its heat of fusion to cancel moles and get kilojoules. So there's that problem. In a third problem, they talk about dumping silver into a calorimeter. That's getting closer to what we're doing in lab, where you have a polystyrene or styrofoam cup, and you're actually dumping the hot piece of silver into the styrofoam cup. Now, the cup itself absorbs some of that energy, and in addition, the water absorbs some of the energy. So you have both the water, so this is the water, and you also have the cup that's absorbing energy. So both of those items, and that's why you have two equations that you have to add together. So considering that, so you have the mass of the water times the specific heat of the water times the change in water temperature. In addition, you're taking the calorimeter constant. So the calorimeter constant is how much energy is absorbed by the styrofoam cup per degree Celsius that is raised, times the change in temperature. So from that, from the first half of the MC delta T, you're going to get joules. Convert that into kilojoules, as you can see. And then for the, for the second line here, I actually took that and got joules out of it, converted it to kilojoules. Okay, so overall, 1.808 kilojoules. Now notice that they want the answer in kilojoules per mole. So what you're going to have to do is convert the silver into moles, and then take your energy that you calculated previously, divide it by the moles of silver, and then you can end up with the kilojoules per mole. And that's it. I do have to acknowledge that these notes, this worksheet was originally given to me by Carl van Vossen of Holland Public. Hopefully you find these helpful. They're very concise, short notes, so I like to use them. Second law of thermodynamics, that's an interesting one. You think about your classroom or in your case, your bedroom, you notice it takes very little energy to just make a mess, and things just have that tendency towards messiness. Well, that's the same thing with what they're talking about in second law of thermodynamics. The big term is entropy. And entropy is always increasing. It is a condition where things just seem to fall apart or go into pieces. A waterfall goes downhill. A lump of sugar dissolves. Ice melts. Gas will expand and sort of disperse. Metals rust. All of these are what we call spontaneous reactions, where it turns out that a lot of it has to do with what we call entropy. And entropy sort of takes you towards this an increase in entropy, or if you have more disorder, then you have a positive change in entropy, or S. So kind of skipping down to here, we're going to be looking for changes in entropy or positive S's where things are getting messier. You can see this measure of disorder when you go from solid to liquid, liquid to gas, 1 mole to 2 mole of substance, systems that go towards higher temperatures. This right here is a thermodynamic chart, much like the one in the back of your book. For the following 3 questions, you can use it to calculate changes in entropy as well as enthalpy. So we'll be flipping back and forth. on page 3 here, if you want to make a prediction, it's pretty easy to do based on the equation, the chemical equation, and then you can also quantitatively calculate the change in entropy to tell whether the system is going towards more disorder or less disorder. So for example, in question A here, magnesium carbonate, which is an ionic solid, very stable stuff, can be heated to where you produce a different ionic solid, magnesium oxide, and carbon dioxide gas. You would predict that you're going to have a positive entropy change because you have 2 moles of product starting with 1 mole, and also because the phase change is towards a more disordered change. So you have 2 things going on that give you that clue. For the calculation, much like calculating for the change in heat, delta H, you would take the sum of the entropy values for the products and subtract from it the sum of the entropies of the reactants. And that's exactly what I do. I get these values from the previous table. I get a positive value, which pretty much confirms that, yes, the system is going towards the greater entropy. You can do B and C on your own. The third law of thermodynamics, just to round off the laws of thermodynamics, lets us know that if you look at a perfect ordered substance at 0 Kelvin, that is the point at which you will have no disorder. So the entropy value, S, would be 0. Alright, and going to the last page. See, I told you this would be pretty quick. Gibbs free energy. So this is the last of the terms that you need to learn for this part of thermodynamics. We talked about spontaneity before, the likelihood that a reaction is going to occur. You can calculate whether a reaction is going to occur under the conditions or not. So we have to consider, for calculating this value G, or Gibbs free energy, we have to have enthalpy, heat energy, we have to have the temperature conditions, and we have to have the change in entropy for that reaction. Now, another term for Gibbs free energy, the reason why it's called free energy, it's the energy to do work. So, we're looking for a negative delta G, and that defines the system as being spontaneous. That tells you the reason why it's a negative sign is because it's work being done by the system on the surroundings. So, for this particular problem here, notice, and again, we're getting values from the table on page 2. Notice that this reaction, I'm going to predict that the combustion of methane is going to have a negative delta G because it looks like we've got a pretty spontaneous looking reaction. I don't know, combustion of gas. Sounds pretty spontaneous. I then look up the values and I notice that, yes, negative 817 kilojoules. That is pretty spontaneous. So again, the delta G can be calculated the way you do, the way you calculate the change in H and the change in entropy. Now, we can look at all the different, this chart here gives you all the different combinations that would give you spontaneous, a spontaneous reaction. Learn this. This is a very important chart. The way to look at it, for example, if you have an endothermic reaction that's going towards more order with a low temperature, I mean, that's like the very extreme, probably this reaction is not going to happen. Okay? And the other extreme would be If you have a highly exothermic reaction that's going towards more disorder, it doesn't matter when, because of the fact that it's exothermic and it's going towards more disorder. It's going to be spontaneous under all temperatures. So this gives you sort of your extremes and a way to look at it. Now, I just want to do number 3 here because it's using this Gibbs free energy equation. And a little note here. I don't know if that note's big enough for you to see, but the major problem in using this equation is your energy values are in different units. So for enthalpy, I looked that up from the previous, or in this problem, it gives you the enthalpy as negative 123 kilojoules. But then all of a sudden they give you entropy values in the tables is always in joules. So what you have to do is take that delta S value, divide by 1,000 so you can have it in kilojoules. And that's what I did here, from here to here. So plugging it into the equation, solving for delta G, I get a negative delta G. Again, this is a spontaneous reaction. The reaction is going to probably occur under the conditions, in this case room temperature. And don't forget to convert temperatures to Kelvin so that the Kelvin units cancel and you have all kilojoules at the end. Alright, so basically I've gone over the very concise notes of Thermodynamics Part 2. You're looking at calorimetry, you're looking at how to incorporate enthalpy, entropy, and free energy into the energy concept or thermodynamics. Alright, hope you have a great day. Make sure that you go back in and do the worksheet that goes with this recording. Talk to you later.